Good evening, everyone, and welcome to our lecture for week 13-14 of INST314. This week, we're going to be focused on simple linear regression. And so before we begin, let me give you a few administrative items. We've got basically 2 weeks of class lecture activity, and then we will be doing our final exam. So this week is the simple linear regression as our topic. We will be meeting on Thursday in our interactive class, and during that class I will be doing an activity that will give us some additional insights on linear regression. And then for the last 20 minutes of the class, we will have a quiz on Canvas. And that quiz will be similar to some of the activity that we did in our last class, where you will have to choose the correct statistical test for a particular situation. There will be probably 1 or 2 questions about linear regression as well, just some of the basics. And that will be mostly true, false, some multiple choice, possibly some matching. At the moment, I don't have an essay, but there might be an essay question. So we'll see about that. For we also have coming up our unit, the combined unit 3 and 4 project, which will cover our multivariate analyses. I will post instructions for those on Wednesday, December the 2nd, and it will be due on Monday, December the 14th. That is the beginning of our final exam week, the week of December the 14th. In between, next week, I will be giving you a lecture and demo on multiple linear regression, and both simple linear regression and multiple linear regression will be on the final exam, so you will want to be sure to take a look at those. At some point during the final exam week, I will offer a review or a Q&A session. Stay tuned for what the scheduling of that will be. Very, very important. Please do mark on your calendar now that we will have a synchronous final exam on Zoom on Thursday, December the 17th. It will be from 8 a.m. to 10 a.m. in the morning. Once again, review materials, other logistical materials will be available as this week unfolds. So for today, we're going to be looking at 3 main things. We're going to begin with what I hope is mostly review for many of you, looking at how we look at potential associations or potential relations between 2 quantitative variables. That's our friend the scatter plot. We measure the strength of that relationship if it's linear with a correlation, and we try to model it with a linear regression. So all of that, I'm going to go through that fairly quickly. It should be, as I said, it should be very familiar to you. If it's not, I invite you to please be sure to do the readings associated with that topic. What is going to be new and a little bit different for some of you is some of the mechanics behind how linear models are fit. And that will include how we do a residual analysis. So that's going to be the heart of what we cover this week. We have something that's called a coefficient of determination, which makes a debut this week and will have a more central role when we go to look at multiple linear regression. We'll look at the impact of potential outliers on linear models as well. And then we'll cover how to do inference with linear regression. So there's quite a bit of material packed into today's lecture. So let's start out reviewing some of the basics. What you recall is that when we've got 2 quantitative variables, these 2 variables, although they're written as percentages, they're not proportions. It's the quantity, it's the magnitude of the percent of poverty and the magnitude of the percent of high school grads that we are measuring and we're comparing, and we're looking for a potential association between them. And what you know is that when we are looking for a potential association between 2 quantitative variables, we represent that graphically with a scatter plot. So each one of these dots is representing a particular percentage of high school grads. These are actually representing particular observations for, you've got 50 dots, 51, because you've got 50 states and DC. And so this is quantifying for this observation. There is a percentage of high school grads is approximately, I'd say that's about 88%, and the percent in poverty is a very small amount, about 7.5. Okay. So when we look at this, what you may also remember is that when we talk about scatter plots, we like to characterize the type of relationship that we see. And so when we do talk about scatter plots, we're looking for what type of relationship we see. Does it look linear? Does it look cyclical? Does it look like it's sinusoidal? Does it look like it's parabolic? All those different shapes. So we're looking for a type or shape of the relationship in our data. We're looking for, if it's linear, we're looking for a direction. Is that direction showing a negative trend? In this case, we're going downward. That's a negative trend. If we're going upward as we go from left to right, that would be a positive trend. And we're looking for the strength of the relationship as well. And so here is a relationship as we look at this particular scatter plot. We see definitely there's a somewhat linear trend here. It is negative, and we see it's moderately strong. How people classify moderately, weakly, weakly as in weakly, indicating strength. How they indicate the strength tends to vary, but I'll give you some guidelines for that when we talk about correlation in just a moment. So here we've got a visual that tells us immediately something about the relationship between two quantitative variables based on the type of relationship that appears to be there, the direction that it's holding, and the strength of that relationship. So when we want to measure that strength, we use the correlation. That's describing the strength of the linear association, and that's highlighted already with color, but I'm going to circle that. Correlations only measure linear relationships. There are values in between -1 and 1. -1 is a perfect negative correlation. +1 is a perfect positive correlation. And in between, there's no linear association at all. Typically, when we're from about 0.7 to 1, we consider that to be somewhat strong. If we're about 0.5 to 0.7, that could be moderate, moderately strong. It's somewhat weak if we're kind of in the range of 0.3 to 0.5. And really, if we're at 0.3, and the numbers are the same on the negative side, from -0.3, +0.3, we're basically weak to non-existent, weak to none. Okay, now these are just general ways to think about weakness. Some people would consider 0.7 to be moderate as opposed to strong. Nobody is going to kick you out of the club if you say that 0.7 is moderate. I would say it's moderately strong. Okay, it's kind of borderline. If you are talking about 0.5, we're talking about something that's kind of moderate, and if it's, we're moving more towards the weak side, right? 0.6, we would have a moderate negative 0.6 here, and moderate negative association here, a moderate positive association. Okay, so once again, that should sound familiar to you. So we quantify using a correlation. One of the things that you'll want to do is to get your eyes accustomed again to looking at what constitutes a certain magnitude of correlation. Here, if you had to guess your best guess for that correlation, you're going to take a look at the direction. And our direction is negative, so that leaves out A and D are not possibilities. If we look at the values here, we see that we have a value that's less than -1, so we can cross out E. So we're really looking at B and C. And so if we look at the strength here, a -0.1 means we almost have no correlation at all. There's no detectable, there would probably be no detectable linear relationship. We clearly have a detectable linear relationship, so by process of elimination, we're going to go with letter B, and it is indeed letter B. We can do the same thing here. This is a different association, percent of poverty, percent in poverty, and percent female householders. Here we see an upward trend, so positive correlation. That eliminates B and C as options. It appears to be there's a distinct linear pattern, so it's not 0.1. We would have a choice between 0.9 and 0.5. If we're at 0.9, it would be almost perfect, and this is not almost perfect, so it's probably 0.5. Okay, and that's what it is here. So I would invite you to take a look at this particular website. It will give you an opportunity to practice. You do your choices and then click the check answers, and it will give you a yes or no, and then give you another set of correlations to look at. But that's one of the ways to sharpen your ability to perceive and approximate correlations. You don't have to do that all the time. You do want to be able to, as I did here, use a process of elimination to figure out what looks like it's probably the correlation. Obviously, in your real analysis, you will be using R code or a calculator to find the correlation. And then finally here, assessing correlation, which of the following has the strongest correlation? Okay, if it's strong, it means it's either strongly positive with a 1 or strongly negative with a -1. And if we look at all of these, what we see is we've got something that's a fairly tight relationship here in A, but it's not linear. B looks very tight and linear. C is very dispersed. D has a distinct linear pattern, but is not as tight as B. So if we had to choose which one it has the strongest correlation, which one is either stronger positive or strongest negative, looking between B and D, B, the points are much closer, and so that would indicate our strongest correlation. I do want you to notice that A, which is kind of a parabolic, looks like it's a parabolic shape, has a much tighter relationship between the points, but it's not linear. So the correlation coefficient would not apply to A. So as we know, we do a scatter plot, and then we try to find a best fit line that will allow us to model the relationship between the two variables. Typically, our explanatory variable is on the x-axis, and our response variable is on the y-axis. Now notice we're talking about an association. We're not talking about causality in this situation. When we write our linear model, you may have seen it written in this form. Y hat is equal to, sometimes it's written like this, A plus B x, just to make things confusing because it's not exactly y equals mx plus b form. So you may have seen things written in this form. We are going to continue with something that's similar to that, but we're going to be changing our coefficients, which you'll see in a moment. But here, once again, we've got our linear model. We've got a predicted value And that predicted value is the predicted value for y is what our model gives, and we signify that it's predicted by using a hat. We have, as we do with any linear model, we've got an estimate for an intercept and an estimate for the coefficient, which would be the slope. And I want you to notice that the slope in this case is negative, which is consistent with our coefficient. The sign, just a reminder, the sign of the slope will be the same as the sign of the correlation. Okay, so we've got a predicted value that is represented by the line itself. Here we go, represented by the line. So everything along the red line is a predicted value of y. It's a y hat. And we have our observed values, which are the actual data points. And as we remember with any linear relationship, our y-intercept is where the graph crosses the y-axis. That's where x is equal to 0, and our slope tells us if we change a unit in y, in this case a unit in explanatory, how much will the response variable increase or decrease. So let's write that for each unit change in explanatory. Then our response is expected to increase. Remember, these are predicted values, so it's expected, it is predicted to increase or decrease by the slope. Okay, and a nice reminder here that none of these statements are causal unless we have a study that is a randomized controlled experiment. Okay. So we've got an expectation, a prediction of an increase in a response based on a unit change in explanatory. So keeping that in mind, let's just go back for a moment to see our equation. We see an intercept value of 64.78 and a slope value of 0.62. So looking at the intercept percent, so let me go back and see this. Actually, I was kind of hesitating here because it does not look right. It's worded oddly. Okay, expected on average to have 64.68% of residents living below the poverty line. When we have a y prime or excuse me, a y hat is equal to a plus bx, okay, and so when x is equal to 0, we have that y hat is equal to a. This value, this y hat value, tells us what is called the expected value of the output. Okay, and in classical statistics, we actually look at it as the expected value of y. That happens to be similar to a concept of average. Okay, so we expect that whenever x is equal to 0, on average, we will end up with an output of 64.68%. Okay, so this is playing off of the concept of expected value, which does not, expected value, which is not really emphasized a lot in your textbook. And so I'm not sure why they're emphasizing it here, but my apologies for leading you astray. So now you know why that answer is as it is. Important thing for us is that even though we calculate the intercept and we've said that we've got a interpretation, sometimes that interpretation is not particularly relevant or useful to us. They're saying here, because there are no states in the data set with no high school graduates, the intercept isn't really valuable in terms of predicting. And we often see that sometimes you have a relationship like between height and weight, and there will be an intercept there, but you don't have somebody who has a 0 height, or you don't have somebody who has a 0 weight to put into the equation. So it's mathematically useful, but not useful in a practical sense. And so I want to emphasize that. So this is speaking of practical, not mathematical usage. Okay, so continuing on. So just a reminder to us that our model is using to predict the value of the response variable, and we're saying also that it's technically it's to predict the expected value, since we went there, expected value of the response variable. On average, the prediction says on average, if I've got 85% high school grads, or if I have 85% high school grads, on average, I can expect there to be 13%, about 12 to 13% poverty level. Let me see if I can get this to be somewhat straight. It's about 12 there. So on average, I would expect that to happen. It just so happens that some of the data points are actually there as well. Okay. So there's some uncertainty associated with the predicted value, and we'll talk about that uncertainty in a moment. The other thing that we want to do here is we're saying applying a model estimate to values outside of the original data is called extrapolation. So this is the domain of our original data approximately. Okay, and here's a line that extends it all the way out to where there's 0. One of the things that we see, for instance, here is that sometimes if this is the original data, okay, if this is the original data, sometimes if we extrapolate beyond there, which is what that blue line does, we miss what are actual trends in the data. Okay, so you want to be careful about not extrapolating too far beyond where your original data set is, because you don't know if the shape will take off and go in a different direction. Okay. Here we don't know if all of a sudden the data goes like this, or maybe the data goes like this. And the same here, we don't know if the data or if information would go like this or maybe like this. It's not necessarily linear when we extrapolate. And this is showing that the idea that the intercept itself might be an extrapolation. It's so far, having 0% high school grads is so far away from where the actual data is that it really is not meaningful. So careful about extrapolation. Don't go too far from your original data. And then there's some an example of this with a news story. I'll let you Google this so that you can see this, but here's the extrapolation that they did from the year 2012. They just drew a straight line out, and this is assuming that the same trend continues over the next 100 years, which is very unlikely to happen. As I said before, we don't know. Here's a slight linear trend here, but we don't know if maybe things will flatten out in a certain way, or if they'll curve downward or curve upward. Okay, we don't have a way of knowing that when we go beyond, if we go out beyond too far out beyond where the original data is. So once again, beware of extrapolation. Okay. So what we've done so far this first half hour should be mostly review for you. Let's talk now about the mechanics and the analysis that we want to employ when we're talking about fitting a line using the least squares regression. So here's our data again, and here are 4 possible lines. It looks like they're counting this line here. A lot of times we can look at the data, we kind of eyeball where we think what line best fits the data. And if you're looking at this, you'll recognize the orange line being the one that we've worked with already. But if you didn't have that previous experience, you might look at this and think maybe the yellow line might be a better fit. It could be. Clearly the black dotted line is not, and clearly the green line really doesn't give us a sense of the data. Right? But we know from previous experience that it's line A because we saw that. We saw that when we were looking at the regression equation. So the idea, so here's our equation again. Here is a representation of what the model would predict for a given state. The idea is that we want to have the line that best, that minimizes the amount of error between the observed values, these dots, and the predicted value. So the preserved, so the error between the observed value and the predicted value is what we call a residual. Okay, and I'm going to write it, the size of the residual is what we see in the observed value minus the predicted value. The predicted value is the value on the line, right? So anything above the line has a positive residual. Anything below the line has a negative residual. You see, in some cases, there's very little residual at all, very small. Some cases, there's very large residual. Okay, so it's a sense of how well does the model pick up that variation, and also how well does the line minimize these large items. Okay, so we're looking for a way to minimize the residuals, which are a measure of the error. Here we have it written here. This happens to show us the negative residual for Rhode Island, the positive residual for Washington, D.C. Okay, it's a type of error. We use E sub I, or sometimes you see epsilon sub I as well, as a symbol to indicate the residual, that error, that difference, right? The difference between what the model predicts and what is the actual observed value. Okay, so Rhode Island has a negative. Okay. So we want to a line that minimizes the sum of the magnitudes of those residuals, or we can minimize the sum of the squared residuals. And it turns out that we typically use the minimization of the sum of squared residuals. One of the things that you'll notice in statistics is that we often use this idea of squaring differences and then summing them or minimizing them in some way. This is what is called the least squares method of fitting the line. We're not going to go into super duper detail on that, but it's just important to know that this is the method that's being used. In the R demo that I show you, I'm going to let you visualize that. It's the most commonly used. You can actually compute it by hand. Thank heavens we don't need to do that for this class, and we're not going to. It's for many applications, the residual twice as large as another is usually more than twice as bad, which is something that we want to take into account. We want to actually have some way of magnifying differences. And so it turns out that the model that we get when we use a least squares line takes this form. This should look somewhat familiar to you. Okay, it takes the following form where we have the predicted value, so that's our y hat, is equal to beta sub 0, which is a intercept value, plus beta sub 1, which is a slope, times the explanatory value. Notice that this y hat is not the response, it is a predicted y value. So it turns out that these betas are parameters, and we can use a point estimate for those parameters. Sound familiar? Of course it does, because this is the same sort of thing that we've been doing with every other type of test combination of variables that we did, where we are interested in a parameter. We're interested in what is the true population intercept, what is the true slope of that line, okay? And we're going to estimate that using a sample. We have a point estimate for an intercept, a point estimate for our slope. And so in the third section of our talk today, we're now in section 2. In the third section, we will talk about how we do inference with those point estimates relative to the parameter. In classical mathematics, we also add a error term onto this to let us know that our least squares, there is some variability with respect to our y hat. There's an error component to it as well. It's not necessarily the residual of the points there, but there's an error term. So I want you to notice this. We've got the same kind of format. So whereas we had a basic linear model, y equals mx plus b, that's a basic linear model. We saw that in regression world, that got turned around a little bit. We had y hat is equal to a plus bx. In this case, b is the slope. That's a regression model. And more formally now, what we're seeing is that y hat is equal to beta sub 0. There's my intercept, plus beta sub 1 x. That's my slope, which I'll underline here. Okay. So you'll want to get your head around this new notation. So this is our least squares, which is a type of linear regression. It's the most common type. It's our least squares model, linear model. So it turns out that if we know the mean and standard deviation of our explanatory variable, this is our explanatory variable, and if we know the mean and standard deviation of our response variable, that we can actually calculate without running software. We can actually calculate the beta sub 0 and beta sub 1. So the point estimate for the slope can be found by multiplying the standard deviation of the response of y divided by the standard deviation of explanatory, which is x, times r, which is our good old correlation coefficient, right? And previously in our slides, we found that that correlation coefficient was negative 0.75. If we go ahead and we take the information that was on the previous slide, just to flash back for you for a moment, S sub y, standard deviation of the y is 3.1, standard deviation of x is 3.73. Correlation we saw was negative 0.75. We can take those and put them together and multiply, and we would get the slope. And then we have that interpretation. for every additional unit change in the explanatory. Explanatory is high school graduation. A unit change is 1 percentage point. We expect that the percent living in poverty to lower because it's negative, lower on an average, or we have the negative here, on the average of about 0.62 points. That's our magnitude of our slope. Okay, so there's a basic interpretation of the slope, and we're able to calculate that using this formula. Our intercept, we're also able to calculate the same way. Once we've got a slope, our B1, a point estimate for the slope, we can get a point estimate for the intercept by taking the average of the y-average and the x-average, and basically multiplying here. You're basically solving an equation that's a linear equation, because we would know that y bar would be equal to b sub o plus b sub 1 x bar. Okay, those would be points on the line. And so if I subtract b sub 1 x bar, y bar minus b sub 1 x bar, I get the intercept. Okay, and so here we can put that information from our problem in, and that gives us our intercept value. So it's actually possible to use those formulas to find it. So we've got a situation now where we're looking at our least squares. Okay, a least squares linear model, known to us as basically a linear, simple linear regression. We see that it's possible to create the coefficient and the intercept by using the basic summary statistics of our y's and x's, as well as the correlation coefficient. Okay, so what are the conditions for us to use a least squared line? Well, the conditions that you see here, here's a nice mnemonic device to figure that out. And we see that the 4 key conditions that we're looking for are that there's linearity, that we actually have a linear relationship, or it appears to be linear, that the residuals themselves are independent of each other, that those residuals are normally distributed, and that there's equal variability in the residuals. Let me make sure that this is of residuals. Okay, so conditions 2, 3, and 4 address the residuals. The linearity, this addresses the data. Okay. So, and remember, we can measure the strength of linearity in data, right, with our correlation coefficient. So an alternative way of looking at all 4 of those assumptions is that we say that our residuals are independent, and I'm going to write it. Our residuals are independent, and they are normally distributed. Sometimes you see this, with a mean of 0 and a constant variance of sigma squared is the variance, and sigma is the standard deviation. You might remember from our normal distribution. I'm going to put a line through that so we know that that's a 0. Okay. And there's a little bit more information on how that, describing all of this in more technical detail at the website that you see here. But we're going to focus on verifying our conditions. One of the things that I'm going to have you note is that for now, we're going to assume independence, although it's possible to check for independence of the residuals. It's a little bit more advanced than our class. There's some plots that you can use here. And once again, if you follow those links, Hopefully, I think that will show up on the PDF. If it doesn't, I'll give you the links as well. But you can follow this so that you can see what are some of the advanced analytic techniques for looking at independence. Okay. For us now, we're looking at conditions 1, which is linearity, 3, which is normality, and 4, which is having an equal or constant variance. Those are the ones that we're going to be checking. We're also going to be looking for outliers, and we're going to see why that's important in a moment. And then we're going to ask our questions ourselves, is an important predictor missing? And so that's where we get into the idea of using what's called a coefficient of determination, or R-squared. So let's look at each one of those in turn. So if we're looking for linearity, when we're looking for linearity, we've got the scatter plot itself, right? So we're looking at the relationship between the explanatory and the response variable and see how closely it tracks to a linear relationship. It says methods for fitting nonlinear relationships do exist. It's not what we're focused on right now. We are focused on the linear types of relationships for our simple linear equation and our simple linear model. And next week we'll make it a multiple variable linear model as well. Okay, so basically you've been checking linearity before. You can look at and find correlations for each of these. Here are 3 different potential linear relationships, 1, 2, and 3. I'm going to tell you that only number 1 is truly a linear relationship, although number 2 looks kind of, but you see that it's got this little weird curve to it. Number 3, that's pretty broad and pretty vague and is not necessarily what we're looking for. Now, what this shows us is that we're looking not only at a scatter plot, but we're looking at these items beneath. And this is something that you see often when we're actually in real life looking at relationships between variables. We're going to look at both the scatter plot of the data and what's called a residual plot. And that's what you see underneath. I'll come back to this picture in a moment after I introduce the residuals plot. Okay. So a residual plot, which looks like this, will typically have the residuals on the y-axis, and it has the fit. It's called the data fit. Okay, what's the predicted value for the data on the axis? And what it's doing is it's saying for every value, like for where's Rhode Island? Rhode Island is here. Okay, so when the X value, which is the percent of high school grads, is 81, here is where the residual is. Okay, so it's telling me the residual for each value of the H values, of the X value. Because it's showing you which value of the X value, it's kind of clear to see when you've got something below and something above. Okay, if you think about it, let's go back a few more slides to this here. It's kind of a flattening of this line where it shows us the residuals. Let's go back here. Where we looked at this, we looked at the residuals. It's almost like taking this line and tilting it so that you then have it exactly horizontal. That's what our residual plot does. So if you look at this residual plot, okay, what you see is basically you'll see the residuals themselves scattered around a line that's at 0. Okay, if it's 0, something at 0 is a point that's directly on the prediction line. Okay, one of the things that we want to see is a nice scatter, a nice, somewhat even scatter of our elements around the line. And here, reading it once again, when my my high school level is 86, this should be 86. Okay, I've got, for DC, I've got some other values that are around that too, but for DC, this represents the residual for DC, which is kind of high. Okay. So if I've got a really good linear fit, I'm going to see something like what's here on the left. I'm going to see a pretty well-distributed scatter, right? There's not really a pattern here in this residual. Unlike over here, where there's a pronounced pattern in the residual. If I've got a pronounced pattern in the residual, I do not have a good linear fit between the two variables. These are two very different examples. Here's one where hand span and height are compared, so that looks like a very good linear fit from the standpoint of a residual analysis, residual plot. Here is a looking at a potential linear relationship between the number of miles traveled in terms of thousands of miles and the depth of grooves that are in the tires of a car. And there's data from 8 vehicles. Notice once again, I don't have a nice scatter in the residual. So that's what I'm looking for. I'm looking for a nice scatter in my residual. That gives me a sense of there being a linear relationship. I'm also looking for there being that scatter to be within sort of a certain window, a certain sleeve, if you will. I'll see that. We'll see that in the next item. Let's just go back here now. We look at this. This has something of a scatter, but we also see that there's kind of clumping in it. So, and we see from the original that it's not a tight linear relationship. Okay, and we know from our correlation coefficient negative 0.75 that it's a moderate to moderate strong, I would say, relationship. Not really super strong, but a moderate strong relationship. Okay, so this is what a good linear plot looks like, a poor fit linear. Okay. We're going to skip over the independent, which is the second condition. We're going to assume that the errors are independent of each other. And you can go back to the previous slide if you want to dig into that more. The next thing we're going to look at is see if the residuals themselves are normally distributed. Okay, we want them to be nearly normally distributed. And one of the ways, remember, we looked at other items. We looked at whether our variables were normally distributed. Now we want to take the residuals. That's a whole different set of data. Okay, those residuals are all of the numbers that come off of this, right? These are all the residuals. It's in our residual plot. All of these dots are a value. That's a residual value. We want to know if those are normally distributed. This actually happens to be a different distribution because I want it to be able to show you that when we look at what you may recall is when we're checking for normality, right? We can check for normality by doing a plot, usually a histogram. Okay. We can do a QQ plot, which is what we've got here to the right. So we've got a QQ plot, or we might run a particular test, and we've talked about certain tests in R that we can run on the data to see if it meets a normality criteria. In this particular set of data, you see that this pretty much falls along. There's a little bit of quirkiness here and there, but it's pretty close to normal, right? It's nearly normal. So this would be, these residuals would meet that condition. The last condition that we're looking at is where we're looking for what's called constant or equal variability. What we're saying is that when we go across the span of the domain of our data, that the variability remains within, for the most part, remains within this sleeve, if you will. I don't have things that are popping way out here or way down here. excuse me, and you'll see that in the residual plot as well. I've got a couple of things that look like they're kind of outside of that. We might consider those to be outliers, and we'll see about that in just a moment. But we say the variability of the points should be roughly constant. This implies the variability of the residuals around the zero line should be constant as well. This is what we call homoscedasticity. Homoscedasticity. There, we got it. So homo meaning the same, scattering, skedasticity. Okay. It says you can check that sort of using a histogram, how spread out is the data, or using the residuals. Okay, here it's kind of when we do a residuals plot, we're seeing that most of the data is pretty evenly distributed between -4 and 4 as the dimension of the variability. They're roughly in this band. Okay, so we're looking for a parallel band that contains our data. That's an important thing. Containing residuals. Oops, that's supposed to be an R. Okay, so we're looking for that parallel band containing the residuals. Let's just take a look here. So here's, let's think about checking the conditions. You know, at the moment we haven't talked about extreme outliers, so that's clearly not a solution to this question. But we're saying, what condition is this model obviously violating? Well, if you look at the model, there's two things. First of all, this shape does not look quite like a linear shape, and we've got some weirdness going on here. We can sort of go up and then down. There's not a sort of nice, even scattering of the residuals. So that's how we know that we do not have a linear relationship, but you see it up here as well. Okay. If we look at this, if you take a look at the residual plot and at the plot of data, what you notice is that the variation along the line gets wider and wider and wider. You have what's called a fan effect in the residuals, or sometimes you'll see what's called a funnel effect. It'll be reversed. It'll be very wide here and funneling down here. When we see something like that, we see that our what's called the constant or equal variability construct is being violated. So we know that that's a difficult situation. Okay. There are, I'm going to discard those ink notations for a moment. So I just want to show you this website, which is that Penn State website that I have referenced earlier. This section 4.4 is a really good section for looking at, this should look familiar to you, for looking at what are things that show up in a regression plot and a residual plot that tell us that we are looking at something that here's a non-constant error. Here's where outliers show up and do something weird. Here's the fitted line. Here's the residual, right? And this is what the outlier looks like. We're going to talk about outliers in a moment. But I just wanted to call your attention to that, to this particular section 4.4, because it gives you some very nice examples of where things don't meet the conditions. Okay, so let's go back into our slideshow. Okay. So, we've looked at this residual analysis. This is super important. We're now that we're doing a little bit more advanced regression than just those basics that we started out with. We want to always do our residual analysis to see how well the linear model works for us. The other analysis that we want to use is our R-squared analysis called the coefficient of determination. It happens to be the square of the correlation coefficient. And the important thing that we want to say is that it lets us know how much of the variability, what percentage of the variability in the response is actually explained by the model. Okay. How much is explained by the model? Okay. When we've got an r squared that is greater than 0.8, we've got a really good model on our hands, right? Okay. In the model that we've been working with, this is actually, you know what, this is an error in the slides. um, our r squared was negative 7.5. So the following the slides that follow this will be incorrect. This came from open source, so we're going to correct them on the fly. So the correlation coefficient that we had was negative 0.75, if you recall, for our data. And then if we square that, we're going to end up with 0.5625. Okay, so that's what r squared would be in our case. What that says is that 56.25% of the variation in the percent of poverty is due to the linear model that we've created. Okay, that linear model is, I'm going to say, is explained by that linear model that we created. Our linear model says that there's a relationship. Here we go. That that the percentage in poverty can be predicted by a relationship that looks at the percent of high school grads. Let me go back to the original. Sorry about that. I just want to, okay, yeah, there's our model. Okay, so it's a model based on the high school grads. So this particular model is giving us 56.26% of the time helps to, well, the 56.26% of the variation in this can be explained by this relationship. Okay, so let me say that again. R squared says that 56.26% of the variability that we see in this variable, any changes in that variable, 56.26% of those changes of that type of variability can be explained by this relationship. That means that there's another 44% or so that's not explained by this relationship. There are other things that affect the variability. Okay, so that r squared, excuse me, that r squared gives us a sense of how well does how good a fit is that model, etc. So 0.56 is a moderate, it's not great. Okay, so our interpretation here is, so these two slides are wrong just because the numbers are wrong. So my apologies. I think when I make a note to myself that when I update these slides, I'll update these slides with the correct numbers and correct the error. All right, so r squared is going to play a bigger role when we talk about multiple linear regression, because one of the things that we're going to try to do is that we're going to want to increase our r squared value. Let me go back to a prior slide where we were talking about some of the things that we look at when we're looking at the, here we go, suitability of a linear model. Okay, so we've talked so far about checking the conditions. This is our residual analysis. And we've also talked about r squared. Okay, So R squared tells us how well it does our current model work. We've got y hat is equal to beta sub 0 plus beta sub 1 x, okay? So we're using x as a predictor, right? A predictor of y hat. If our R squared is very high, then that x is a good predictor. Good if R squared is fairly high. I'm going to use about 0.8, right? Even 0.75. Okay, that's pretty good. If we want to, in our case, we found that our R squared was approximately 0.56. Okay, so we might want to improve that. Since we're seeing 0.56, we might think, hey, maybe if I add a predictor, I get a better fit. That's what that R squared tells us. So I'm foreshadowing for you what we're going to do next week. But that's why we're doing the R squared. Is this a reasonably good fit? If it is, fine, then this is a good model. If it's not, maybe we need to add some predictors to our model. Maybe we need to add another predictor to our model to improve the R squared, to improve the fit. Okay, so we've looked at those. Let's look now at our outliers. Okay. The types of outliers that we see in linear regression. Okay. How do outliers influence our least squares line? Well, sometimes it can totally change our line, sometimes not. Okay, so we need to think about how would the regression line work with or without outliers. And you can see the residual plot too, how the outliers look like they're way out here to the end. Here we got the outliers here. They are horizontally separate from the rest of the data. Okay. If we did not have the outliers, would the regression line be steeper or less steep? You know, if we drew a line through here without the outliers, not taking them into account, maybe we get something like this. Still negative, but perhaps a little bit steeper. Okay. So we want to know what happens when we get rid of the outliers, right? Okay. So we classify our outliers several ways. Notice that with this particular outlier, that outlier draws our regression line upward and at a very relatively steep level. Okay. Without the outlier, if we took this outlier out, we would find maybe a line that kind of went like this. Okay, so not so much of a relationship. So this was an influential outlier. It influenced the linear relationship. And since it influenced the linear relationship, perhaps it's something that we want to exclude so that we can be more accurate. So here's some terminology that we have. All right, so what are our outliers? Outliers are points that are distant from where the mass of our points are. If they are horizontally away from the center of the mass of our points, we call them high leverage points. And high leverage points that actually change or influence the slope are called influential points. So we see previously, it's way away, it's a high leverage point, and it's influential as well. On our prior, here are some things that are high leverage. They're away from the mass of the data. They're somewhat influential, but not as influential as we saw in the other data. Okay, so we've got influential points. So how can we tell if a point is influential? Well, we've got to basically exclude the outlier from our data and take a look at the slope of our line. Does it change considerably? Here you've got something that's pretty dramatic, where you've got these outliers to the left, and then the mass of data, if you think of the center of mass of the data is here. If we include the outliers, we've got a negative regression line. Okay, notice those, it's influential. It pulls the regression line upward here to the left and then down to the right. If we exclude these outliers, we've got a very different relationship, right? We've got a positive relationship. Types of outliers. Here's an outlier that is away from the mass, but if we took it out, if we took this out, it wouldn't very much change the relationship. Okay, so it's high leverage because it's away, but it's not influential. Okay. And if we look at this one, here is an outlier here. Does this outlier influence the slope of the regression line? That we would actually have to run it, not by much, it says. Okay, so here's the original. It's kind of hard to see. It's not going to necessarily, because we've got all of these points here, it's not going to necessarily pull the line down in this direction. And if you look at the scatter here is pretty evenly distributed, okay? And then there's this one little thing. So that's not going to be a heck of a lot of a difference in our residual, in our plot. Look at the difference here. This is kind of lined up within the sleeve, okay? As compared to, where's the other? When we've got this situation, everything's masked here, and then this is out along the side. Okay, once again, this is sort of training. You have to train your eye, taking a look at the examples. Oops, I gave you the answer here. Which of the following is true? It turns out that none of them are true. Influential points always change the intercept of the regression line? No. Influential points always reduce R squared? No. It's much more likely for a low leverage point to be influential than a high leverage point? Not necessarily true. And when the data set includes an influential point, the relationship between the explanatory variable and the response variable is always nonlinear. So none of those are true. I'm going to invite you to just take a look at those and go back and see what we have here. And I invite you to also take a look in your textbook to take a look at the discussion, which I will flag for you. Discussion in open intro textbook with respect to influentials and other influentials in high leverage. That's a very good discussion for you to be familiar with. Okay. So here we've got, this is the situation we saw before, where we have a high leverage and influential point, okay, which basically that point gave us a high a high correlation coefficient and a high R squared coefficient of determination. Okay, although in reality there's no relationship here, right? Here's a low R squared, low R squared. Okay. Without that outlier, we see how very much there is no distinct linear relationship. Okay, so that high influence point gives us all kinds of weird information. So let's round up here. I'm hoping that we'll round up in about another 10 minutes. Thank you for sticking with me through this. It's kind of like 2 lectures in one. Inference for a linear regression. So we kind of hinted at this before. Let's look at it in context. So we've got the setup here. I'll leave you to read everything in the setup. What we see is an explanatory variable of biological IQ and a response variable of the Foster IQ. Okay. Data set, IQ scores of identical twins, one raised by foster parents, the other by biological parents. And so we're looking at the correlation of IQ. So we're wondering how much is genetic versus environmental. right? If it's environmental, it's the parental influence. If it's they're twins, so there's genetic. So if we think it's pretty much genetic, we expect to have a high correlation. We've got a linear relationship here, it looks like, and we've got an R. R, remember, is our correlation coefficient of 0.882. Very strong correlation, right? Nice strong correlation, and a positive, strong linear relationship that looks like it's there. It's not perfect, it's not the absolute perfect, but it is pretty nice here. I want you to notice that there's good variability around the predictor line as well, right? Things seem to be fairly evenly scattered. Okay. So running a program, the following information was given in the program. Looks like I've got a little floater. Let's discard that. Excuse me. Here we go. Okay. So let's go back into our current slide. Okay, there we go. All right, so running a computer program, we get the following information. Okay, so this, we see here the line here is the coefficients. This is our estimate for the intercept, b sub 0. Okay, so that estimate is here for b sub 0. So b sub 0 is equal to 9.2760. This shows me an estimate for the slope. Here's my estimate for the slope. That's b sub 1. Okay, notice how I'm reading this. This is giving me the estimate of my parameters. Okay. This is giving me a standard error in my estimate for the parameters. B sub 1 is 0.90144. And then what I also see here is a t-value related to my estimate. Doesn't this sound familiar? And a p-value, the probability of being greater than, the probability of seeing something that's greater than our t-value. Right, so it gives me a p-value here. We'll come back to that in more detail. So just pointing things out here. Residual standard error is not something we're going to get into a lot. We've got these values that are related to r squared, okay? And this f statistic is going to become more important to us when we have multiple, okay? So here's our r squared and our adjusted r squared. When we talk about multiple, we'll talk about our adjusted r squared. But right now we're just going to be, let me just look at that, okay? So it looks like almost 78% of the variation in foster IQ, foster twins IQ, can be accounted for by the model that's got the biological twins IQ. So this is a pretty good fit, very, very good fit. Okay. Our linear model, using this information, our linear model is going to be that the foster IQ, that's what we're predicting, is going to be equal to the intercept, 9.27, plus the slope, 0.9 times the bio IQ. Okay, so that's the model that we've got here. So what's, sorry, yeah, so my apologies. It's obvious that I'm kind of tired doing this. I'm sorry that I'm making those mistakes. I see what it's trying to do here. Which of the following is false? Roughly 78% of the foster twins IQs can be accurately predicted by the model. No, it's said incorrectly. What it's saying is that 78% of the variation that we see in this, okay, can be accurately accounted for by this. Okay, so this is a very precise distinction that's being made. Okay. So when we're doing inference, okay, and this is what we're doing here. What we're doing when we're doing inference related to linear regression, when we're doing inference related to anything, we have a hypothesis. And so our hypothesis, when our hypothesis is testing for the slope, which happens to be b sub 1. Okay, so when we're doing inference with linear regression, okay, our inference is always that the null hypothesis is that basically there is no linear relationship. Okay, that there's no linear relationship. And our alternative hypothesis is that's not true. We have a meaningful slope, that there is a linear relationship. Okay, so we're wanting to reject the null hypothesis and show that there's a statistically meaningful linear relationship. Okay, and hopefully we'll not be making mistakes here. So yes, because of the parameters. Okay, so our hypothesis is written in terms of parameters. And let's go back and correct that. So it's beta sub 1. And our B's are what we have as our test statistics, right? Okay. So this is the same information that we saw here. Okay. So what we're doing is we're testing to see, is this a statistically significant slope, okay. In other words, do I have a linear relationship? We don't really care about the intercept when we're doing inference, because it doesn't necessarily have a true meaning. It's really the slopes are my predictor. We're wanting to know, is biological IQ a good predictor of the Foster IQ? So we're always doing t-tests. Here the t-value is 9.36, and it's got a p-value that's like super small. Yeah? Okay. We know what happens when p-values are super small. Okay. So we've got the test statistic. Notice that we can create the test statistic in the same way that we have previously. Okay. Our point estimate is B1. That's the observed slope. Okay. The degrees of freedom here are n minus 2 instead of n minus 1. Okay. And so that's where you get the 9.36. Here's the calculation, right? So we're taking the observed value minus the null hypothesis divided by the standard error. That gives us our t-value. We're going to look up a table or put it in R for degrees of freedom of 25. And what we find is that we get a p-value that's very, very small, 0.000. Okay. So that means that we are going to reject H sub O, that the slope is statistically significant, and therefore we have evidence for a linear relationship between the bio IQ and the Foster IQ. Whoops, IQ. So that's how we are doing inference with linear regression, our inference is relative to the slope. Let's look at another example. Can we say there's a relationship between the percent of college graduates and the percent of Hispanics in a sample of 100 zip code areas in LA? Here is, if we look at each of the 100 zip code areas, we look at there seems to be a negative linear relationship. We can actually take a look at that more closely. When we run a linear model, we get an estimate of our intercept and our slope. This is the slope. This is a point estimate for the slope, point estimate for the intercept. Okay, and so what we're saying in terms of a model is that the prediction for the percent of college educated is going to be, here's a linear model, 0.729 minus 0.7527 percent Hispanic. This is in LA. That's the linear model that we have estimated. Okay, so 1% increase in Hispanic residents in a zip code area associated with a decrease, a 7% decrease in percentage, 75% decrease in grads, 0.075% decrease in grads, an additional 1% decreases the percent of college grads in a zip code area by 0.075%. A zip code areas with no Hispanic residents, that's talking about an intercept. So we're looking at here, and it looks like we are looking at B, an increase of 1% is associated with a 0.75 decrease in percentage of grads. How reliable is this if the p-value, if the zip code says, do these data provide convincing evidence there's statistically significant relationship? We're going to be looking at this. That p-value is exceptionally small. So yes, there seems to be convincing evidence. How reliable is this? It's not very reliable if they're not randomly selected, right? Okay. Now, one of the other things that happens is not only do we do the hypothesis test on the slope, but we can also, a lot of output will give you a confidence interval around the estimate. And that confidence interval is the same thing that we've seen before. There it is, point estimate plus or minus margin of error. And we remember that we have point, why is it giving me letter B? Ah, it's the t-value. You guys, I hope you're doing bets on how many errors I'm making during this thing. Okay, so my apologies. So I'm looking at I'm looking at a z value. Remember, we need to find a t for 95%, 95% and degrees of freedom equal to 25. Okay, so that, which is not something that we have sitting here in front of us, is going to be the 2.06. Okay. Okay. There we go. And so that is looking at it. All right, so we are almost at an hour and 30 minutes, which is quite a long ways in. So let's just recap a little bit. Our hypothesis test, we basically, for a single predictor linear regression model, a single predictor. Okay, that means we have y is equal to, um, let's do the actual population model, which is beta sub 0 plus beta sub 1 x. X is the predictor, it's the explanatory variable. That's a single predictor, explanatory variable. And really we want to know, we're interested in, is this non-zero? That's what we're interested in for our inference. Okay, so the hypothesis test, we do the same sort of hypothesis test that we had before. You're going to get a printout with a t-value and a p-value, and you're going to say, do I reject? So my h sub o is b, beta sub 1 is equal to 0. H sub a is that beta sub 1 is not equal to 0. And based on your t-value and your p-value in your printout, the t-value being calculated the same way that we calculated before, we're going to either reject or not reject the null hypothesis. A lot of times, if we've got a good model, obviously we're rejecting and we're saying, yes, there is a linear relationship. Yes, this is a good predictor. So this says no lin relationship, not good predictor. And this says yes to all of those things. Yes to a linear relationship, and yes, good predictor. Doesn't say how well it predicts. Okay, and we can say what is the size, the confidence interval gives us the size of the slope, right? This is an estimate of true population slope. Okay, the null value is often 0. We're checking to see if there's any relationship. Regression output gives us a two-tailed p-value. Okay, so we're not looking if it's greater than or less than. We're not saying it's at a negative or a positive slope. Okay, we rarely do inference on the intercept, which is what I told you before. Okay, so we'll be focusing on estimates and inference for the slope. Okay, that's what we're interested in. And when we branch into multiple variable, we're looking at multiple slopes, multiple predictors, and that's what we'll hit next week. Always be aware of the type of data you're working with. Random sample, non-random sample, or population. Statistical inference and the resulting p-values are meaningless when you already have population data. You don't need that, right? If you have a sample that is non-random or biased, inference results will not be reliable. And the ultimate goal is to have independent observations. All right, so we're going to stop here. I've kind of maxed out my voice and my energy for today. So I'm going to, I do have a nice short little R demo for you where I'll go through some of these conceptual items again. A lot here for you to review. Once again, I want you to make sure that you're solid on the basics of the linear regression, which is the first part, that you are beginning to understand the residual analysis. Of course, you're going to need to understand that by the time you get to the final exam. So I'll give you some things to practice with. Residual analysis, what that R squared means, taking a look at outliers, so all of that. And then we quickly went through the inferential. So on Thursday in class, I will hit that inferential again and also highlight some of the crazy nuances with respect to interpretation that that I kept bombing out on in today's presentation. So thank you for your patience with that, and hopefully a little bit of good humor as well. And we will, I will see you tomorrow, or whatever day it is that you're viewing this, with the demo related to R. So that'll be posted on Tuesday. This will be posted on Monday night. Thank you again, and good studying.